Good afternoon, everybody. So, in the previous classes, we are discussing about the noise performance of different amplitude modulation techniques. And we have seen what is the signal noise ratio and what is going to be the noise figure of the AM or SSB or the SPSC system. In this class, we will discuss about the performance of the frequency modulated systems with respect to the noise that we are going to have. As we have seen in the case of any sovereign receiver, them also will be using as a sovereign receiver. And to calculate the signal noise ratio of the receiver, we said that we started with the IF filter, and then from there we have seen for the AM modulation up to the baseband filter. A similar block diagram you can see for the FM reception also, wherein we have the input with the signal and the noise with the power frequency eta by 2, and the IF carrier filter we are going to have it with the carrier filter HCF, and then after the input we should know that the frequency modulated signal will not have a big variation in the amplitude. So what are the modulation signal that we are going to have that has been converted into the variation in the frequencies. Therefore, the modulation is going to be there only in the frequency, whereas the amplitude is constant in the case of frequency modulation. Therefore, we will be using an amplitude limiter so that if at all any noise, white noise that has been added, a white Gaussian noise that has been added in the channel can be eliminated or reduced to the maximum extent by going for this amplitude limiter. And after that, we are going to use a band pass filter to get back the signal with the frequency variation that we are going to have it according to the baseband signal that we are going to have it. Then we have the FM discriminator, wherein we have a frequency to amplitude converter, which will be basically a differentiator that we are going to have it, and then the envelope detector that we are going to have it. So combinedly, these two blocks of frequency to amplitude converter and envelope detector will form our frequency modulated discriminator that we are going to have it. The output of this envelope detector is given to the baseband filter, with the filter to having the base frequency response as we require based on the requirements of the frequency that we are going to have the maximum. And in the baseband filter, the baseband signal that we assume to be the maximum value of what is that of the FM. So we will be having the required baseband filter. And we are assuming that the input signal SIT is going to be A cos omega ct plus K integral m of tau d tau integral minus infinity to t that we are going to have it. So that will be the frequency modulated signal that we are giving as the input, with the input power SI that we are going to have it is A square by 2, because the magnitude of the signal that we are receiving is A. Therefore, the input power that we are going to have it is A square by 2 that we are going to have it, and the white noise that we are going to have it is the power frequency density eta by 2 that we are going to have it. So the signal power is A square by 2, and the power frequency of the noise, the input, is going to be eta by 2 that we are going to have it. And we have the IF carrier filter with the sufficient bandwidth that we are going to have it. So in the case of AM, we said that this IF carrier filter is having the bandwidth of 2 FM, whereas in the case of FM, we know that the bandwidth that we require to transmit the FM signal is going to be 2 into beta plus 1 into FM, or 2 delta F plus 2 FM that we are going to have. So the bandwidth that we require for this IF carrier filter is going to be 2 delta F plus 2 FM that we are going to have. So this is what plot that we are going to have it, the center frequency FC, and the bandwidth of the carrier filter that we are going to have it is this B. The bandwidth that we are going to have it is 2 delta F plus 2 FM, or 2 into beta plus 1 into FM that we are going to have it. So we are having the required bandwidth for this carrier filter, which is much higher than the bandwidth that we require for a typical AM receiver that we are going to have. In the case of AM, we said only that of 2 FM, whereas here we are going to have the bandwidth as 2 delta F plus 2 FM that we are going to have it. So that has been given to the amplitude limiter, so that the very amplitude variations in the input signal because of the A2 noise that has been there in the channel can be eliminated, by using this amplitude limiter. So when we are discussing about the FM detection, we have seen a typical circuit for an amplitude limiter, but basically we can say that this amplitude limiter can be a simple flipper also, a two-sided flipper that we are going to have with the transfer characteristics like this. So if the input is going to be more than this, then we are going to have the constant amplitude, and similarly if the input is going to be more than particular amplitude, the amplitude is going to be constant, whereas the small changes in the amplitude is going to be linear, that we are going to have it, what are the variations that we are going to have it. But typically, we know that there are no variations in the amplitude in the small signal, but whereas any increase in the amplitude can be eliminated by this limiter that we are going to have it. So the output, when we are giving a signal like this, a sinusoidal signal, so the output of this limiter that we are going to have give you the spurious signal that we are going to have it, along with the frequency variations, whatever we are going to have it because of the modulation that we are going to have it. Therefore, the noise variations, if at all, are going to be there more than this amplitude, will be eliminated, and we are going to get a constant signal here like this. Therefore, whatever the noise that has been added in the channel, we can eliminate it by using this limiter, or sometimes we may call it as hard limiter, so that all the amplitude variations are going to be eliminated. And this limit, we can reduce it so that even the input signal is going to be reduced. Still we are going to get a constant output only. So we will be designing this limiter circuit appropriately to eliminate whether the increase in the amplitude or decrease in the amplitude, so that we are going to get a constant amplitude at the output of our limiter. And whatever the variations that we are going to have it, only because of the frequency variations. So time variations are going to be coming here, and this has been given to our baseband filter that we are going to have it in this one. And this baseband filter, because we are having a tuned circuit, this square circuit once again gives back your sinusoidal output that we are going to have out of this baseband filter that we are going to have. So the input signal for this baseband filter is the amplitude limit is Va of t, and that has been converted into V1 of t. So the output of this band pass filter we are denominated as V2 of t. So this is having the required frequency variations or the modulation that we are going to have it. That has been given to the frequency to amplitude converter that we are going to have it. So this frequency to amplitude converter, we are going to have it as a linear variation in this bandwidth that we are going to have it. And within this limited variation, the amplitude is going, frequency is going to be converted into the amplitude variations that we are going to have. So as this frequency from the center frequency Fc plus or minus, the amplitude increases or decreases from this center point that we are going to have it. Therefore, the frequency variations have been converted into the amplitude variations by this frequency to amplitude converter that we are having. And this will be nothing but, as you are looking into this, the frequency variations are converted into amplitude variation. This is linear function that we are going to have it with the output as sigma into the frequency that we are going to have it. Therefore, this typical performance of the circuit, we can say that is a differentiator that we are going to have. Anyhow, we will look into that analytical part a little while later. So this is the differentiator that we are going to have, which is going to convert our frequency variations into the amplitude variations of our frequency modulated signal. So that amplitude variations are given to your normal envelope detector, so that the amplitude variations have been, only the amplitude of the envelope of this is given as the output, which is going to be giving you the baseband signal along with the higher harmonic signals that we are going to have, along with the DC signal. So this baseband filter will eliminate all the other unwanted frequencies except this baseband filter having the 0 to FM frequency that we are going to have it. Therefore, we are going to have this frequency response of your baseband filter from 0 to FM. So all the frequency components in the baseband signal has been passed through this baseband filter, and we are getting required output from this baseband filter. So this is the typical frequency modulated receiver that we are going to have with the requirement for the calculation of the noise that we are going to have. So as we have said that we are having the limiter and this discriminator to convert your frequency variations in the input signal because of the noise has been related to the limiter, and whatever the frequency variations because of the baseband signal has been converted into the amplitude variations, and then these variations have been passed through your envelope detector so that only the envelope of the signal has been obtained, and then we are getting the required baseband signal output, which is going to be required variation that we are going to have it. So this signal, we'll see that what will be the analytical part that we are going to have it from this block diagram that we are going to have it. So we can say that the typical function of this frequency to amplitude converter, we'll say that this is going to be h of f having the linearly with the frequency over a limited range in the bandwidth theta that we are going to have, that is 2 delta f plus 2 fm is the bandwidth that we require. So in this limited range, the frequency is going to be varying linearly with the amplitude that we are going to have. The frequency increases, the amplitude increases linearly, so that the output will be converted into the frequency to amplitude variation that we are going to have. Therefore, the typical transfer function of this frequency to amplitude converter, h of j omega, we can say that simply sigma j into sigma omega that we are going to have, where sigma is a proportionality constant that we are going to have. So as the frequency changes omega, your h of j omega changes. So if we take this magnitude, so these frequency variations are going to change as the magnitude variations that we are going to have it. So coming back to the time domain signal, that V3 of t is going to be sigma d by dt of V2 of t. V2 of t is the input to your amplitude frequency to amplitude converter, and the output of this frequency to amplitude converter is V3 of t. So as we are saying that it's j of sigma omega, j of omega gives you d by dt of a particular value. As we know that Fourier transform, differentiation gives you j into omega, therefore this j omega is nothing but a differentiator d by dt that we are going to have it. Therefore, this V3 of t, the output of your frequency to amplitude converter, V3 of t is given as sigma d by dt of V2 of t, where V2 of t is the input. And let us say that the sigma of d by dt, as we are saying that d by dt gives you j of omega. Therefore, the frequency domain representation of this time domain signal sigma d by dt is j into sigma omega. The frequency domain representation is j into sigma omega, which is nothing but a differentiator and the time domain signal that we are going to have it. And let us say that the input signal that we are going to have it, the V2 of t, is a cos omega ct plus phi of t, the cos unmodulated carrier omega ct plus the angle variations with respect to the phi of t that we are going to have it. So, and this AL is the limited amplitude of the input, which is going to be constant, because as we have seen in the previous class that we are going to have it, the amplitude of the signal after the limiter is going to be constant with respect of the input variation that we are going to have it. So this is having a constant amplitude in the output that we are going to have it. Therefore, that is going to be the AL that we are going to have it. So this V2 of t is going to be AL cos omega ct plus phi t, which is given as input to your frequency to amplitude converter. So and AL is the limited amplitude of the input, because A is the input that we have assumed, and that has been passed to your limiter, so that output of your limiter is going to be giving you the AL. So what are the noise variations, because the channel noise that has been added is eliminated, and we have got a constant amplitude, and only the frequency variations are represented in the time domain waveform that we are going to have. Therefore, this V3 of t, the output of your frequency to amplitude converter, V3 of t is sigma AL into omega c plus d by dt of phi t into sin omega ct plus phi of t that we are going to have, because this is AL cos omega ct is V2 of t, and we are having sigma d by dt of V2 of t that we wanted. So this is sigma AL into differential of this cos theta that we are going to have, it is omega c plus d by dt of phi of t, and the differential of this cos is sin omega ct plus phi of t that we are going to have. So this is the output V3 of t is sigma AL omega c plus d by dt of phi of t into sin angle that we are going to have. And we are assuming that now value alpha equal to the sigma into AL that we are having, so that we can simplify this instead of writing always the sigma in AL, we can write simply the alpha value. So with this substitution of alpha value equal to sigma into AL, this d4 of t that we are going to have it the output of the envelope detector that we are going to have, because in this g3 of t is the input to the envelope detector, and the amplitude of this signal is going to be, this is the sinusoidal signal, and the envelope is only sigma al into wc omega c plus d by dt of it. Therefore, v4 of t is nothing but this amplitude of the sinusoidal signal. So that is nothing but sigma al into omega c plus d by dt of phi of t that we are going to have. Expanding this into this alpha omega c plus alpha d by dt of phi of t that we are going to have. So this is the DC component that we are going to have at alpha omega c, and this is time varying signal that we are going to have at d by dt of phi of t, which is coming as the output of our envelope detector that we are going to have. Thus, the discriminant output V4 of t is proportional to the frequency of the input d by dt of phi of t that we are going to have. So this d by dt of phi of t is nothing but the frequency modulation that we are going to have it in our signal that we are going to have. So look back to our frequency modulation dc that we are going to have it, which gives that d by dt of phi of t is nothing but our amplitude frequency variations that we are going to have. Therefore, the discriminant output V4 is proportional to the frequency of the input d by dt of phi of t that we are going to have. So we have converted the frequency variations into the amplitude variations and obtained the output as that frequency that we are going to have. So from this we will calculate the different noise powers and signal powers to get the signal noise ratio of the frequency modulated signal that we are going to have. So we will see that what will be the signal noise ratio that we are going to have it, and to get that first let us say that what will be the signal power that we are going to have it. So the signal that we are assuming is Si of t equal to a cos omega ct plus k integral minus into t m tau d tau that we are going to have it. So this is the time varying signal that we are going to have it. M of t is our baseband signal, which is modulating our scalar signal cos omega ct that we are going to have it, and this SIT is your frequency modulated signal. So M of t is the required baseband signal that we have to recover from this frequency modulated signal, and the bandwidth that we are going to have it is beta is b equal to 2 delta plus 2 fm, because of the constant rule that we are going to have it with the frequency, the maximum frequency of the baseband signal is f of m, and the deviation that we are going to have it is delta f. Therefore, the bandwidth is equal to 2 into delta f plus fm, or 2 into beta plus 1 into fm that we are going to have it. So this input has been passed to the amplitude limiter. Therefore, the S2 of t, the output of the amplitude limiter, is going to be AL cos of the function that we are going to have. This is the A that we are going to have with the input, and what are the variations? The amplitude variations have been eliminated and have a constant amplitude AL by this amplitude limiter that we are going to have. Therefore, the output of this S2 of t, which we are written in the block diagram as V2 of t, is the signal that we are going to have. It is AL cos omega ct plus k into minus infinity plus infinity m tau d tau that we are going to have. So in this one, the phase angle that we are going to have, phi of t is going to be k into minus infinity m tau d tau that we are going to have. So that's what we have seen, that the definition of this gives you the frequency variation that we are going to have it, and therefore the S4 of t or the V4 of t in the block diagram is going to alpha omega c plus alpha k into m of t that we are going to have, because this alpha omega c plus alpha d by dt of phi of t. So d by dt of phi of t is equal to k into m of t. Therefore, the output of your envelope detector is going to be alpha omega c plus alpha k m of t that we are going to have. And with the baseband filter, eliminating the DC signal that we are going to have it, considering only the baseband modulation signal that we are going to have it, the output signal that we are going to get after the baseband filter is going to be alpha k into m of t, by eliminating this DC signal alpha omega c that we are going to have. Therefore, this is the signal at the output is going to be S naught of t, is going to be alpha k into m of t that we are going to have it. Therefore, the signal power that we are going to have it is the mean square value of this, so that is alpha square k square, and mean square value of m of t, that is m square t average value that we are going to have it. Therefore, this is the signal power S naught is equal to alpha square k square m square t that we are going to have it. So this is the power that we are going to have it, and this is the signal power that we are going to have. So if we calculate the output noise power also, then we can calculate what is going to be the signal to noise ratio that we are going to have it. So in order to get this signal noise power that we are going to have it, the input white noise we are having with the power spectrum density eta by 2. So we are now calculating the output noise. The output power that we are going to have, signal power is going to alpha square k square m square t. And to get the output noise power, we are assuming that the power spectrum density of our input signal is going to be eta by 2 that we are going to have it. And the noise output is independent of your modulated signal m of t, because we assume that this is a constant amplitude, and then having only that the carrier signal that we are going to have it. Therefore, the output noise we can calculate with the baseline signal equal to 0 itself, that is a cos omega ct that we are going to have it. That's why the input signal and with the noise that we are going to have it is a cos omega ct plus, this is the in phase noise signal, and quadrature phase noise signal that we are going to have it is a cos omega ct plus nct cos omega ct minus nst sin omega ct that we are going to have, where nct is the in phase quadrature amplitude, and nst is out of phase the quadrature output nst, that noise signal that we are going to have. So that the total input signal as far as the noise is concerned is going to be a cos omega ct plus nct cos omega ct minus nit nst sin omega ct that we are going to have with m of t equal to 0. Therefore, the magnitude of that we can get it as a plus nct of cos omega ct minus nst of sin omega ct that we are going to have come, because this is a cos omega c and this is nc cos omega ct. We are rewritten as a plus nct cos omega ct minus nst sin omega ct that we are going to have. So that has been represented here in the figure. This is the amplitude A is your a cos omega ct, and to this we are having the in phase signal ns or nc of t that we are going to have. So that the total amplitude in phase signal is going to be a plus nc of t that we are going to have it, and the perpendicular signal, the quadrature signal is going to be ns of t that we are going to have it. Therefore, the resultant signal that we are going to have it with the noise and the signal by a cos omega ct is going to be rt that we are going to have it with an angle theta of t that we are going to have, where this amplitude of this rt is going to be root of a plus nct whole square plus ns square t that we are going to have. So this is the amplitude of the a square plus b square that we are going to have the root. So this is the r of t that we are going to have it. This is the diagram what we have seen. So this is the magnitude of this vi of t that we are going to have it is root of a plus nc of t whole square plus ns square t that we are going to have. Whereas the angle theta t that we are going to have it is tan inverse of ns of t by a plus nc of t that we are going to have. So we are having the magnitude and phase that we are going to have it. Therefore, v of t that we can represent as the magnitude r of t plus into cos omega ct plus theta of t that we are going to have it. Therefore, this is the input signal va of t that we are going to have it, or the output after the amplitude limiter, because of the noise signal is going to be v2 of t equal to al cos omega ct plus theta of t that we are going to have it. So this is the noise signal according to the output of the amplitude limiter that we are going to have it. And here, as we have seen, that the v2 of t that we are going to have it is a2 cos omega ct plus theta of t that we are going to have. And we know that this ns of t and nc of t are very small compared to your amplitude of the carrier signal that we are going to have it. Therefore, looking into that consideration that we are going to have it, with the signal to noise ratio, we assume that it is very high in the case of the frequency modulation signal that we are going to have it, or that means that this nc of t is very small compared to a, or the quadrature signal also is going to be very small compared to the a that we are going to have. That is, nc of t and ns of t both are much smaller than the amplitude a that we are going to have it. Therefore, the tan theta that we are going to have, because theta is going to be very small, because nst by nst plus a is the tan inverse of that is the theta. So therefore, when theta is small, tan theta is going to be theta only. Therefore, theta t equal to instead of nst by a plus nct. So nct is neglected and theta t equal to nst and NST by A that we are going to have. So this is the theta angle that we are going to have it because NST is going to be very, very small. Therefore, the V2 of T, that is the output of your amplitude limiter because of noise, we can represent as AL cos omega CT plus theta T. I have represented this as NST by A that we are going to have. So the output of the amplitude limiter is going to be V2 of T is AL cos omega CT plus NST by A that we are going to have it. And in the equation previously that we have seen for the noise power that we are going to have it, this NST by A is nothing but your pi of T that we are going to have it. Therefore, the output of your LF detector D4E is going to be alpha into omega T plus 1 by A d by dt of this pi of T or NS of T that we are going to have because NFT by A is going to be what? Pi of T. So alpha into omega T plus 1 by A d by dt of NST will be the output of your LF detector that we are going to have it. And this output of LF detector is given to the baseband filter, eliminating the DC component so that the AC term that we are going to have it is alpha by A into d by dt of NST that we are going to have it. So this is the nice voltage that we are going to have it with the power spectral density that we are going to have it. The power spectral density that we are going to have it is eta for this NST that we are going to have it. In the last class we have seen that NC of T and NS of T with the spectrum being limited to beta by 2. We have seen that this is eta that we are going to have it. So the differentiation represents as sigma j of omega, therefore alpha by A j omega that we are going to have it as far as this noise is concerned. Therefore, this G M4 of T that we are going to have it is the eta that we are going to have it, the power spectral density of the noise signal that is going to be eta. So that's what we are going to have it, and the bandwidth that we are going to have it is B that we are going to have it, so that is plus or minus B by 2. So this is given to your frequency discriminator, so that is the differentiation that we are going to have it. Therefore, J alpha omega by A that we are going to have it. And this is passed to your band pass filter. Therefore, when we have this nice power spectral density as eta, after this differentiation, this is Gn4 of F that we are going to have it with the H of J omega being J alpha omega by A for this noise signal that we are going to have. Therefore, the power spectral density output of this differentiator is going to be square of this signal alpha square omega square by A square into eta that we are going to have. So this Gn4 of F is the output the power spectral density of the differentiator that we are going to have it. That has been passed to your band pass filter from minus FM to FM, the baseband filter that we are going to have it. And as we have this as the power spectral density, when we integrate over the entire interval from minus FM to FM, then we are going to get the nice power that we are going to have it. This is the N0 that we are going to have it. So this is the power spectral density Gn4 of F, which is going to be equal to alpha square omega square by A square into eta. Therefore, the noise power that we are going to have it is integral of this power spectral density over the range minus FM to FM, because we have the baseband filter having the frequency response from minus FM to FM. So when you substitute this and integrate it, we are having alpha square eta by A square into integral, and this omega square are written as 2 pi f whole square that we are going to have, so that 4 pi square f square into df that we are going to have. Therefore, with this integration that we are going to have, because this is minus fm to fm, this is an even function. Therefore, 2 into 0 to fm, 4 pi square f square df will be coming as fm and q by 3. Therefore, the total noise power that we are going to have it will be coming as 8 pi square by 3 alpha square eta by a square into fm cube that we are going to have. So this is the noise power that we are having at the output of your baseband filter that we are going to have. Whereas the signal power is alpha square k square m square t that we are going to have. Therefore, we can see that the ratio between this signal to noise ratio, where S0 by N0 is going to be, and we have seen that S0 is going to be alpha square k square into the mean square value of the signal m of t. and the noise power that we are going to have it is 8 pi square by 3 alpha square eta by a square fm cube that we are going to have. So this is the signal noise ratio that we are going to have it is, as well as the frequency ordered discriminator that we are going to have it. This we can rewrite it as bringing back this 3 to the numerator, and then this one of the 2 that we are going to have it I am writing as a square by 2. Therefore, this signal to noise ratio at the output can be rewritten as 3 by 4 pi square. In the k square, average value of this k square value m square t by fm square into a square by 2 eta fm. Because I am writing this a square by 2, because this a square by 2 is nothing but the input signal power that we are going to have it. And this eta fm that we are going to have it is the input noise power that we are going to have it, that is the capital NM, and suffix m that we are saying in the case of the amplitude modulation. So this is the a square by 2 by eta fm gives you the signal noise ratio at the input that we are going to have it, but this output signal to noise ratio that we are going to have it. Therefore, this is the equation that we are going to have it, as well as any signal m of t that we are going to have, objective signal m of t. So this was S naught by n naught, and the output signal noise ratio is going to be 3 by 4 pi square k square m square t average by fm square into a square by 2 eta fm that we are going to have. Instead of the arbitrary signal, let us say that this m of t is a sinusoidal signal cos omega mt. So therefore, that means that Si of t we can say that a cos omega ct plus delta f by fm into sin 2 pi fmt that we are going to have, where delta f is the frequency deviation that we are going to have. So this is R. This delta f by fm is nothing but your beta value. So a cos omega ct plus beta sin 2 pi fmt that we are going to have, and this is your frequency modulated signal that we are going to have it when we have m of t is cos omega mt that we are going to have it. Therefore, after differentiating the